Hey guys, it's good to see everyone. I feel like most of you already know. Yeah, most of you know me or have talked to me at some point. Most of you know me or have talked to me at some point. But just for sake of tradition. My name is Hari. I am going to be giving this talk per hour on. I titled it "Topics in Applied Computer Science," but that's a very vague title because there's a lot of things that fit into applied computer science. So basically, like all computer science. So more specifically, I actually thought a lot about what I wanted, kind of the scope of the. Oh yeah, by the way, since it's a small crowd, you can feel free to. I'll have the chat open, so you can feel free to just type questions into the chat, or just start talking. Yeah, just start talking. Like, I won't mind if you interrupt or anything like that. The idea of this presentation is that it should be kind of like a conversation. So yeah, which is especially good since it's a small crowd this time around. But yeah, anyway, with that, like I was saying, I have thought a lot about kind of what I wanted the scope of this talk to be, kind of the different things that I wanted to go over. So I made you guys a kind of table of contents. Yeah, so basically this rather talk is like kind of a nice computer salad of different grad classes that I took over at some point in my life. The compilers class, that's actually a great one. I recommend it to everyone who I can. Unfortunately, print prog is a prerequisite, so if you're not planning on taking that, then like you can't do this. But yeah, for anyone who's taking print prog and kind of likes that stuff, then it's definitely something to consider. It's you can actually skip the first course. Yeah, like the first course in the grad sequence, you can get grad compilers 1 and just go usually straight to grad compilers 2, which is what I did. Anyway, that's usually better because compilers 1 is. But yeah, anyway, especially I'll kind of get into this a little bit and kind of elaborate on it a little bit, and like once I actually start talking about this. But compilers is kind of split into like two halves. The one, there's kind of programming language theory. Not only like there's kind of language theory, and there's kind of computability theory that defines like the stuff that we kind of talk about and mean about all the time, like Turing machines, different languages, that kind of stuff, like from a mathematical perspective. But there's also this programming language theory, really kind of what differentiates different languages, how you can implement different programming languages, how you can implement compilers for them, what like a compiler really is for that matter, from like both an engineering perspective and kind of a theoretical / mathematical perspective. Questions like that. The first like 20 minutes of my talk is basically going to be like about half the grad class in like what kind of role does it play in computer science, what are some ways in which it's going to impact and advance the future of computer science, so on and so forth. Aside from that, also be talking about like kind of hardware computer engineering. You can think of that kind of subset of the talk as kind of grad comp arc, that and kind of comp arc framed in a much more interesting way. One of the interesting applications of like the kind of hardware side of things is there's a lot of interesting stuff going on in gaming, like just eyeballing out of this crowd. I know Sean and Soraver like play a lot of video games. I know Jonathan plays a lot of video games, any of you, like I imagine there's a large group of people. In computer science that do that kind of thing. So that'll be a really interesting side to explore of all of this. And finally, I'll just be talking about this is something that I kind of just threw in there because why not? But I also kind of wanted to talk about the internet side, the kind of networking side of things, just kind of at a foundational levels, kind of how computers talk to each other. You would have learned some of that in systems, some of that in like an IT class. But the areas that I'll be generalizing it to, those have more to do with what are some interesting areas in academic research concerning networks, right? What are some things that you can do? What are some open problems in the field? How can you take those open problems and kind of generalize them in a way to make them interesting for like, just generally for us in the scope of just consumer tech, right? Like our laptops, our desktops, our video games, and so on and so forth. So yeah, with that introduction in mind, I think we can actually kind of get started with the talk. So yeah, so like I mentioned, the first part is just kind of going over what a programming language is at a foundational level, kind of at an existential level almost. What a compiler is, what a compiler is, once again at a foundational perspective. So yeah, I can get started talking about that. So I titled this slide as Inside the Black Box, which is an homage to some book that Sean sent me about, whatever the hell Sean talks about, finance. Yeah, that was anyway. That was the Inside the Black Box thing was actually the title of a book that someone wrote about. Yeah, about just kind of HFTs and how those work. So I kind of stole the title a little bit. I shamelessly plagiarized it to kind of title this slide to talk about just compilers. A lot of people see compilers as just a black box, like you run a bash command or you click a button in Eclipse, you click a button in IntelliJ, and then your code compiles and somehow runs. Nobody ever really takes it beyond that. Nobody really takes it and thinks of it beyond that. And sometimes for good reason, right? Because compilers, especially in the field of especially to people who are like a little bit more on the theoretical side or a little bit more on the a little bit like really kind of get into it, like take the 400 level classes and grad classes in school and just work on like the really back end and low level stuff in the industry as opposed to JavaScript and so on. As opposed to JavaScript and some of the higher level things. Anyway, the point is like there's a large group of people in the field who see compilers as just kind of a black box. There's a lot of people kind of in the know about compilers who very much want that to not be the case, because if you understand how a compiler works, it ultimately gives you the propensity to kind of use it better. You can debug things in new ways. You can debug things more effectively. You can find bugs that otherwise you wouldn't have found before. You can integrate your compiler with other components of software that give you some really interesting features and functionalities. I'll talk more on that later. One thing I do want to note is that compilers in the context of this talk is completely different from interpreters, right? An interpreter is at a foundational level. It takes one component of the compiler, and I'll go over the components like literally in the next bullet point. But it takes one component of the compiler basically stores your program as a data structure in memory, right? And then it just kind of loops through that data structure. You can think of it like a graph. It just like traverses that graph and like kind of does something in each step, like it interprets it, so to say, right? And to an extent, like that graph traversal is your program. You can represent an arbitrary program as just kind of a graph, right? Right? That's actually called a control flow graph, which is a concept that I'll be touching on in a second. But anyway, I like to think of interpreters kind of as a subset of compilers, right? The compilers also have this theme of taking your source code and storing it as a data structure in memory so that you can kind of do things to it. But compilers take it a step further than that, right? The characteristic is that not only do you store it as a data structure in memory, but you reason about that data structure, right? You optimize it. For example, if you have you can do some really expensive things in the optimization space, which I'll touch a little bit on, but I can't really get too much into. But in any case, I'll just go over I'll start by going over like the different kind of components of a compiler, the compilation stack, if you will, like the same way web dev has a stack and that's why you can say front end versus back end versus something else. Compilers, networks, and basically like every complex component of software has a stack, right? At the highest level of that stack is what you call a parser, right? The parser is responsible for, you can see in this diagram that I have here, the parser basically encompasses the first three steps of the analysis, right? Your lexical analysis, your syntax and semantic analysis, That's all taken into the parser. Basically, what those fancy words mean is that you have a program. In most cases, it's actually an auto-generated program. You don't usually write parsers by hand. There's parser generators. There's pieces of software where you can just type in something that's called a grammar, like a specifier for a language, and then that will generate you a parser, right? In C or some other language, that will generate you some code to parse your code and kind of represent it as a data structure in memory that you can use in other places in your program. So first you have this parser. You just read your program as kind of as a string, kind of as just like bytes from your disk. And then through multiple phases, you do different kinds of analysis on it, and you represent it as a graph in memory, right? And when I say graph, it can take the simpler compilers, the ones that aren't necessarily that complicated. It's literally a graph just with your like adjacency linked list of pointers or whatever, however you do it. But in some other more complex compiler infrastructures, there's actually an intermediate language here. You'll see that in the intermediate code step of this kind of diagram. The symbol table, by the way, is something I'm not really going to get into. It's a very fucky mechanism, one that doesn't really let you do anything interesting in the context of this talk. But I can get into that later if some people want to know about it. But but in kind of the more complex compilers, as I was saying, you take instead of an in-memory data structure, you can represent it just as like its own program in kind of an intermediate language. So the high-level idea is that a compiler is something that translates a source-level language into a target-level language. Your source-level language can be C, C++, Java, whatever language that compiles, and your target language should be usually it's whatever instruction set that your computer architecture supports. So for Intel processors, that's x86. For AMD, that's something else, and so on and so forth, right? Those instruction sets, those are, from a technical perspective, and I'll go over that more later. From a technical perspective, those are still languages, right? But the high level idea is that you translate your source language to your target language. So the most important step to kind of doing that is your parser, which kind of lets you take your source level language and represent it in memory. After that, you have an optimization step. Optimizers are very complex mechanisms, which is why, for sake of time, I won't really talk about them as much as I could. But the idea is that you can do some algebraic optimizations. You can take complex calculations. If some guy writes A plus C, and then in the next line A minus C, like A minus equals C. If a guy were able to write that, you could just eliminate that whole thing, eliminate that whole block of code, because the compiler would be able to analyze that plus C is directly the inverse of minus C. And since one thing happens right after another, you don't really need that section of code. Similarly, if there's unused variables, your compiler will basically just ignore them. If there's if you declare a variable once every time in the loop iteration, sometimes it'll just take that variable out of the loop. A lot of small things that kind of add up. So at the system level, it's a lot cheaper. It's a lot easier to do them, right? That's the job of your compiler. That can get kind of algebraic, so to speak. That can get just generic for any language. And it can also be architecture specific. Different architectures can support different specialized instructions, which I'll also get more into. But finally, there's kind of a code generator, right? It takes your optimized data structure, your optimized abstract syntax tree, your AST, right? That's the data structure that I talk about that represents your program in memory, right? It takes that data structure and then it outputs runnable code, right? And once again, that runnable code can be x86, it can be JVM bytecode, whatever you have, whatever target language you have. But I hope with that you can kind of get a high level idea of kind of looking inside this black box, right? Looking at the big picture of how a compiler translates a source language into a target language. So a little bit more on that. What I not only did I want to talk about compilers as software, but just to kind of do the next kind of inductive step and just kind of generalize this idea that we have about compilers. I also wanted to briefly kind of think of them as a mathematical structure. First, you'll have to talk about, before you can talk about a compiler for a programming language, you'd have to talk about what the programming language in general is. a programming language in general is, right? So just kind of formally speaking, if you've taken discrete or if you've taken like, algo or so on and so forth, like I think like I had my professor kind of briefly went over this, but in algo actually, but you have to have something called you have to have something called the syntax. The syntax is it's what's called a grammar. It's basically a set of rules. It's basically a set of rules that you can use to construct just kind of words, so to speak, just kind of members in the language. So in this case, like kind of valid programs, right? There's rules to create a valid program, and there's a set of semantics, right? And semantics just at a very non-rigorous, at a very like kind of hand-wavy level, they define how programs relate to each other. Right? Like if you have one program and another program, can you combine both of them to create the same, create like a third program that's, can you combine them to create a third program that's actually equivalent to the first two? Can you, like what's the, like things like defining meaning in each syntax element and so on and so forth. In order to have a programming language, you not only have the syntax is kind of the obvious part of it, you also need a set of semantics, right? You also need some meaning associated with each of them, right? That's just at a very, there's actually no like widely accepted rigorous definition of programming languages in the field, but this is just like a valid one for what most people do with it that we can use. There's also no rigorous definition of what a compiler does, but you can think of just programming languages as sets of programs, right? And a compiler, like an ideal compiler, so to speak, is just like a literal function that just it's a mapping that maps your programs in your source language to an equivalent program in your target language. And I say equivalent because they're supposed to do the same thing. An ideal compiler would ensure that that your program semantics are exactly preserved, right? You could preserve the exact behavior of the source language. So there's no kind of information lost in the compilation step. So to give you an idea, if you interpret your source language, or if you find some way to run a code in your source language without the compiler perfectly, your compiled code should do the exact same thing as your source code, right? It should exactly preserve the semantics. So one other insight to kind of go over here is that a complete programming language, and I say complete to mean Turing complete. If you know what that means, good for you. Like it's good, but like just at a high level, if you have if statements and you have recursion, you can represent any program that that the current computer that we have today is capable of simulating. You can have if you have a set of rules like expressive enough to do that. If you have a set of rules expressive enough to kind of symbolize, to kind of encode if statements and recursion, that's all you need to specify any program in existence, right? That's just one kind of key insight that I wanted to go over here. But the high level idea is that you have a mapping between your source language and your target language, and you can think of each language as just like a set of programs, right? So each program in your source language maps to a program in your target language. You can think of it just like a function from discrete 1 or 2. You can discrete 1 or 2 or in the math class, or hopefully you get the idea. You can also think of it as kind of like a translator, right? You have your source language, which is designed for humans, and then your target language, once again, x86 or ARM, something like that, something that's designed for a computer to read, right? And the compiler is kind of the translator. It's the mapping between the two of them. That kind of, once again, an ideal compiler translates them exactly. Real world compilers, they're written by humans, so unfortunately, like something somewhere is always going to have a bug. Compilers are generally just like as software, they're very stable. So if you tell a compiler writer, if I go and tell the developers of GCC that they have a bug in their code, like it's very serious business. It's very serious business because that happens very, very, very rarely, and they have extremely rigorous test suites to do that. It's the most it's almost like you can think of it, a compiler, even as like mankind's most correctness critical piece of software that you can write. So it's they almost never ever have bugs, but like once again, they are written by humans, so it does like kind of happen. So one key theme that I kind of went over in the earlier slides is semantic analysis, right? And the idea of semantic analysis is that there should be some you want to look at the semantics of your program, right? You not only have a syntax for your program, but each instruction has some kind of a meaning. Each which is not present in just like a normal syntax, or not just like a normal grammar or the set of rules for constructing a language, like constructing the grammar itself. With that, you don't get like any notion of meaning, right? So in order to kind of analyze this meaning, you, of course, the first logical component of software to automatically analyze the semantics of code in a certain programming language is the compiler itself. It kind of has to do that to represent that code as kind of a data structure as it does, but that code kind of as a data structure as it does. But we also use that kind of principle in a lot of different things. We use that in autocomplete, just like if you type in your editor, just like system.out.println. If you just type in like the SYSO, it'll complete the print line. That feature actually uses autocomplete. It uses a string searching algorithm to just look against your syntax and just match against the possible things that you could complete to. It reconciles that with your history. It does a lot of things, and then just match you with the top and most kind of likely results. Go to definition, like if you've ever been in VS Code or IntelliJ, and you've just been able to right click a method and just right click like a method call and then just go to the implementation of the method. That uses a similar kind of analysis. Same thing with real-time warnings. Like as you're typing, the IDE or the editor will tell you exactly what's wrong with your code, right? The reason most of these features are possible in kind of a scalable way is that modern compilers, they not only keep the parser as a crucial part of the compiler itself, they also kind of expose the parser as an API. So you have direct access to this component of software that analyzes the semantics of your program. They can tell you in very loosely speaking, it can tell you what your program means, right? And if you have like kind of a server, like if you kind of have like kind of an API, like something over a network maybe that gives you that, you can do real-time code analysis, which is really under the hood, like what enables these features that I was talking about, those features and like a lot more. So I'll give like these things all the honorable mentions throughout these tasks. Throughout these things, like I did Model UN at some point in my life, and in Model UN, an honorable mention was when you won an award, but not really. It's kind of just it's just something I use these to just mention like in this talk to like kind of just mention important components of software. Yeah, important components of software that kind of have to do with whatever I'm talking about, right? So case in point, this honorable mention just goes to Microsoft's language server protocol. It actually does exactly this. You can take an arbitrary compiler, and if that compiler, the parser of that compiler, to be more specific, if that implements a certain protocol, if it exposes a server in a certain protocol, VS Code, usually it will be able to call out to that compiler. It'll just be able to like send it JSON requests, like as you can see in this diagram, through RPC. It would be able to send it like RPC requests through JSON is what I mean. But and it would be able to get an idea of your kind of code analysis through that. Right, you can see in this diagram that the development tools, so VS Code or your debugger, what have you, just kind of talks to the language server, which is usually a component of the compiler. To implement it, sorry about that. It's a component of the compiler. Just turn this off. It's a component of the compiler, but yeah. So that's one cool piece of software that uses this theme of. You guys can still hear me, right? Hello?
Yeah.
Okay, cool. Yeah, didn't want what happened last time to happen again, but yeah, so that's the kind of high-level theme of this. That high-level theme of the language server protocol. I mean, you can have a server that implements a certain protocol, and your dev tool, your VS Code or what have you, will talk to that server in real time and give you like real-time analytics over your code. So that's one cool thing that's kind of happened in this field of compilers. There are many others that are possible. The field of compilers and like programming languages more generally speaking, just kind of interact with a lot of other fields that provide you with some cool things. for example, there's some cool things you can do with compilers in the distributed systems area and the database areas to give you these very complicated databases that do a lot of really cool things, solve a lot of difficult problems really quickly, like quickly with respect to speed, memory constraints, and so on and so forth. So we're gonna talk. Yeah, I was gonna talk a little bit about like the hardware and like the kind of computer engineering side of things. The idea is that this is a field that we as computer scientists, as opposed to computer engineers, rarely ever get to talk about or think about. But it's good to think. It's good to think about it. It's good to know what's going on in this field, this kind of a high level discipline, so that because once again, that part actually has a lot to do with compilers. Your compiler is actually like even lower. You could think of it as even lower level than the OS. It's the only component of software that writes code to directly like. It's the only component of software that's responsible to kind of write code, so to speak, right? It's the only component of software that directly directly translates your code into code that directly programs the hardware. So in some sense, the compiler is actually the lowest level piece of software you can get. So you can imagine that it would have a lot to do with hardware, right? So the advancements in hardware actually in some cases necessitate, in some cases give rise to some advancements in compilers. So that's one reason we should think about this. Aside from that, there's just like a lot of cool stuff going on in this area that I wanted to mention. Once again, you can kind of think about this segment of the talk as kind of grad comp arc, right? Not only thinking about the things that you would learn directly in comp arc, some of it is just a restatement of that. Other parts of this is just like kind of open problems in this architecture / engineering area, right? Like directions in which the world is going to, kind of solve those open problems and push forward the science. So, yeah, here I have a picture of the ENIAC, the ENIAC, which is the first computer ever built. You can see that, like, you've probably seen this picture before. Like, it's definitely if you take a computer architecture class with, say, Santosh, or if you like really watch any kind of lecture about like computers at an existential level, this is the first picture they're going to show you, like the ENIAC, the first kind of computer ever built. It holds up to kind of what they say about it. It takes up the whole room. Like, I think the memory device itself is like kind of, the whole thing was supposed to cost like 500K, like 500K, like before inflation. It was a massive research project. It was actually the first kind of Turing complete component of hardware. Complete component of hardware that could, so to speak, simulate any program that you can possibly write, given this model of a computer, right? I titled this slide "The Generalized Computer" because a lot of things are computers when you wouldn't think they are. Like, you have the obvious ones. You have your laptop, your desktop, your cell phone even, right? But in some cases, your internet router is a computer, right? It has a processing unit. It has a processing unit that parses your packets, figures out where to send them, and then forwards them. That forwards them, right? It has a processing unit to do that, and it has some memory to do that with. So in that sense, it's a computer. At that point, you could also look at some Amazon delivery drones. Those are also computers in that they're programmable devices with their own processing units and their own memory. You could also, Facebook also has like this kind of aerial fiber deployment system. I actually, like, I know a kid who actually went to Rutgers, who worked on that team during his internship at Facebook. But the idea is that, like, you have this kind of plane that flies around like really high in the sky in these kind of underdeveloped areas, and then just give them access to like high quality wireless internet. Presumably so that they could go on Messenger and talk to their friends, and so that Facebook could serve them ads, and like you get the idea. But yeah, anyway, this kind of component of hardware exists. You could think of even these things as computers, as opposed to just your generic consumer hardware that you usually think a lot about, your laptop, your phone, and so on and so forth. But more than that, what I wanted to address is kind of the commonality between all of these devices, right? At a generic level, like what existentially speaking makes a computer. So there's actually a lot of contradicting definitions about that. It's not one thing that you can rigorously quantify. nobody's ever bothered to because the field of computer architecture and the field of kind of engineering in this area like didn't really need them to. I just yeah, because of the lack of a rigorous definition, but still the need to kind of existentially quantify it. Yeah, to kind of like existentially quantify it at a very kind of low level. You could generalize some properties that computers usually have. So the first thing that they usually have is like some notion of an instruction set, right? Once again, in the case of Intel processors like x86, in the cases of AMD, like I think it's yeah something else. So something else like the AMD instruction set. But the common characteristic between them is that they all support what's called the fetch, decode, execute cycle. Right? It's a cycle where for each instruction, the processor should fetch it from memory. Right? There's this predetermined location in memory specified by what's called specified by a number in the register in a special register that's called the program counter. Right? In each kind of clock cycle, if that phrase means anything to you. In each clock cycle, you're supposed to read a certain instruction. You're supposed to fetch it from memory and store it in your registers, right? And your registers are these segments of memory, these very small segments of memory that's very quick to access for your CPU. They're like right next to it, physically speaking, right? So you fetch it and store it in your registers. Then you decode it, right? Like they're very simple instructions. It's usually just each instruction is just kind of represented by a number, and you have some kind of instruction vector, like it's like a hash table in an array, like some kind of instruction vector to just figure out what those instructions mean and which registers / memory locations they correspond to. That's the decode step. First you have to fetch it, then you have to decode it. Finally, you have to execute it, right? That instruction has to have some meaning. You have to, yeah, if the task is to like move instruction, you're supposed to be able to move the memory location specified in one register to that specified in another register, or you're supposed to do some pointer arithmetic, or like maybe some complex math operations in some of the more complicated architectures. Speaking of complex architectures, one thing that I kind of wanted to do, like a mention of, is there are two kinds of machines. There are RISC machines, reduced instruction set computers, and CISC machines, so complex instruction set machines. This theme of reduced versus complex instruction sets is very important with computers because some hardware, it corresponds to the kind of hardware it is. If you have a laptop or if you have a desktop, some massively complicated machine that puts the ENIAC, this machine that puts this kind of thing to shame, some massively complicated machine with a dedicated CPU, a dedicated graphics card, a network drive, and so on and so forth, that would usually take CISC instructions, so complex instructions. It would make sense to have a larger set of instructions, each meaning and doing a very specific thing, as opposed to a reduced instruction set where, like, if you had a router or something that isn't really supposed to be doing a lot, maybe doesn't even need an operating system, or if you have like a delivery dome, something like that, you get the idea. Something that doesn't really have very complicated hardware, you use a reduced instruction set kind of architecture, right? So there aren't that many instructions. Yeah, there aren't that many instructions. You can just it's a very simple thing to implement and a very simple thing to maintain, which is preferable for if you don't have complicated hardware. It doesn't really make sense to have support a complicated instruction set. So yeah, that's one kind of distinction between those two things that I wanted to make note of. But yeah, you have those two common characteristics in a computer, but at the highest level, or the lowest level, depending on how you think of it, you need some notion of a processor, usually a CPU, something that executes instructions from a specified instruction set. And you need some notion of application memory, something where you can store your data, something where you can store your data, however small that is, or however impersistent that is. You don't necessarily have to have a hard disk. You just have to have like something that corresponds to RAM, right? Something that's there for the processor to index and execute computations over. So at a generalized level, like at a kind of existential level, hopefully that helps quantify computers a little bit in terms of kind of what they are, what they do, like kind of what they are and what they do, what properties and what mechanisms they're supposed to support. Yeah, so you can look at that, but I also wanted to talk about the characteristics of some modern kind of computer hardware. Here in this picture, you can see like what I think of as kind of like the bastion of kind of really high performance, really complicated modern computer hardware. This is a gaming CPU. Yeah, this is a gaming computer. You can see that it has multiple case spans. It has yeah, it looks like an Asus motherboard there. It looks like an Asus motherboard there. I don't think I see a graphic card, but yeah, maybe I'm blind, but yeah, so you can see there's a water cooling loop, and yeah, basically this is a very complicated machine designed with several like multiple compute units, right? There's the CPU, there's definitely a CPU in there. You can like it might have a graphics card. Maybe the guy is waiting for the 3080 and it hasn't shipped yet. But yeah, you have multiple compute units, multiple processors. Yeah, multiple processors, right? And several I/O devices. I/O devices are kind of weird. They're kind of computers in and of themselves. They're kind of computers in and of themselves. For example, each of your hard disks, right? Each of your HDDs or SSDs, each of them actually have their own CPUs, right? And those CPUs are responsible to look at your main memory, figure out, like talk to your main CPU, like look at your main memory, figure out which file operations to perform, and then just perform file operations for that specific disk, right? Sometimes they talk to the CPU directly. Other times they talk to other I/O devices. You can talk to you can think of any I/O device as like kind of a peripheral device that's apart from your main CPU and your main memory that kind of does something ad hoc, right? In this case, do disk operations. Do disk operations, write something to disk, or do operations, right? Like decode an analog signal and do so on and so forth. The idea is when you have all this stuff, right, when you have multiple CPUs and multiple graphics cards, each of them consuming a lot of power and being responsible to do a lot of stuff, doing a lot of stuff like play Final Fantasy 14 or, like run Minecraft with all the mods in existence, you would need a lot of power and a lot of cooling, right? So the cooling theme, this is actually, it's good that I mention it, because this is actually a custom water cooling loop. This is a custom water cooling loop in the game, in the gaming system. You can kind of, this is about as high level and as like obscenely complicated as it gets for just kind of computer cooling. Probably also uses a lot of power if it needs that kind of cooling. Usually when you have power, you need more heat, and heat's very bad for your computer parts, so you need some kind of mechanized system to cool them, right? Usually an air cooler, but sometimes like this, sometimes a water cooler, right? That's kind of on the performance end of things. That's something that you would use for like a very complicated laptop or a very like high-end, very complicated gaming rig, something like that, right? On the other side of things, there's also kind of embedded systems, right? In this side, you can think of like Apple Watches, VR headsets, components of hardware like that, like computers like that, so to speak, that are designed for a very specific purpose. There are real-time embedded systems, right? Things that are supposed to communicate with you in real time. Your cell phone, your smartphone, the latest iPhone or the latest Samsung Galaxy, that's actually considered an embedded system, right? It's a specific kind. It's a real-time embedded system that supports an operating system in this case, whether iOS or Android or something else. That's a characteristic of embedded systems. Some of them support operating systems, others of them don't. And out of the operating systems, some of them aren't real time. Like some of them are meant to just very very like kind of at a high level just interface with the hardware. Not really do anything more complicated than that. Others are responsible to like talk to a user and work with a user in like kind of real time. Different operating systems to different cases. So that's one thing that you could talk about. You could also have standalone operating systems, mobile, a lot of different things you could do in this area. But the idea is you don't need hardware except for a very specific purpose, right? In fact, it's actually bad to have hardware more than what you need. That kind of quantifies more than what you need, right? On the other hand, like if you were building a gaming PC and like you bought like an unnecessarily expensive graphics card, which I am very likely going to do. If you buy like an unnecessarily expensive graphics card, the worst case is you don't use it and you only end up using half the memory on your graphics card or like half the compute power and so on and so forth. But in an embedded system, it's actually mission critical if you don't do that, if you include too much hardware, right? If your drone doesn't fly or if your complicated telesurgery system doesn't work and the guy on your telesurgery table, your remote surgery where the surgeon is in a remote location, when I say telesurgery, if you're in that kind of situation using an embedded system and something fails, like the hardware doesn't work as it's supposed to, and it's hard to debug because you have too much of it. Like someone's life is on the line, the guy dies. So, and the point that I'm trying to drive is in the case of embedded systems, you have very specific hardware and you have very little hardware, like the bare minimum of what you need, not even like a little bit more. Not even like a little bit more. It's not like a laptop where you can buy more or less than what you need, more or less than what you need. It's actually mission critical that you only have a little bit. So let me just look at the time here. God damn it. Okay, yeah, but anyway, okay, yeah, so yeah, yeah, so, one other final thing that I wanted to talk about in this kind of hardware related area is like I kind of mentioned before, there's some kind of hardware related compiler advancements. The most important compiler advancement that I can kind of give reference to is LLVM, the low level virtual machine, right? Eventually someone came up with the idea that every time you have a new compiler, you don't have to implement like a code generator for the same architecture once again. For example, GCC was the first kind of commercialized commoditized compiler to do this. But GCC is massive and it supports everything from x86 on your laptop to x86 on your laptop and some very very reduced instruction set in like a packet switcher, and like the packet switching component of a router, or some very very small, very very like kind of low, like kind of very low resource utilization kind of embedded system, right? Yeah, so GCC was the first one to do that. It's the most mature compiler in this aspect. Mature in that it's been there for a long time. It supports just about everything, which is good because the first thing you do when you design any kind of respectable programmable hardware is you implement a C compiler for it. So it's good that GCC does that, right? GCC supports almost basically every every instruction set exposed by every piece of programmable hardware known to man, right? And like I'm talking like calculators, smartwatches, so on and so forth, right? But at the kind of next level is that the problem with GCC is that if it only supports some small set of languages, you can have C, C++, you can have Objective-C, but like you can have a couple others, but nothing more than that. If I wanted to implement my own programming language today, it would be very hard for me to use GCC's system to do it with. It would be really hard for me to expose it as a GCC front end, write my parser, right? I would have to write my own optimizer and write my own code generator, which is a very, very big hassle, which is why actually most people don't get into hitherto didn't get into programming languages, right? Get into this field of software design and research, just because there was such a big bottleneck to implementing support for every architecture that your user might want to use, right? So in a nutshell, there's LLVM. LLVM is a piece of software that basically generalizes that, right? They basically say like, we'll design a code generator for every architecture you can think of, x86, PowerPC, ARM, like that's just the ones on this list, right? They'll also design the optimizer for it. The only thing that you have to do is design a programming language that parses to LLVM IR, right? And the IR, you can basically think of it as the AST. Like I said, in some of the more complicated compiler infrastructures, your AST isn't so much a kind of a graph in memory with your kind of adjacency linked list or anything like that. It doesn't look like that. Your IR is basically like a full-fledged language in and of itself. You can kind of encode it as a string and just output that to the user. That's actually one way you can debug if you know LLVM really well. You can output the LLVM IR and see what's actually going on with it. For some very hard to find bugs in some very low level programs, that's actually a thing that they do, right? But basically this IR, which is basically the AST, LLVM exposes that as kind of an API. And what your job is as a language designer is, your job is to just design the parser that parses your language to LLVM IR, and then just throw that at LLVM and it'll do the rest, right? The most common languages, off the top of my head, there's definitely a C++ compiler that uses LLVM, but yeah, I know Haskell uses it. I know there exists a Haskell front end for it. I don't know if the main Haskell compiler uses it, but the main Rust compiler uses it. The main Swift compiler uses it. Swift is Swift being the iOS language. like language for a lot of iOS development that you see popping up these days, kind of the successor to Objective-C in a lot of ways. But yeah, initially became successful in part because they used LLVM. So LLVM is a very big, very important piece of software in this area. It's made possible. It's given rise to. It's made possible a lot of different advancements in programming languages. It's the main reason that you see newer languages that are kind of trendier, right? That are kind of trendier and newer and offer you a lot of features and like a lot more simplicity that the old languages didn't, right? And the key characteristic is when I say any target language, I mean like literally almost any target language. I could write my own language that targets a JVM, right? You could compile Java with LLVM if you wanted to. It could target that, right? It could, it could target like not only and the idea is not only that, it's also a native language. You can support any architecture and like you can write theoretically like the fastest programming language if you wanted to. You could write a programming language that's as fast as or faster than C if you wanted to. It would be hard to do that, but you could. So aside from this theme of LLVM that I've been kind of talking about, there's also another important theme is kind of better hardware utilization. Like I said, in a lot of spaces in consumer hardware, you have kind of more hardware, more powerful hardware, more specialized hardware, right? For example, you can get graphics cards that you can get a graphics card like online if you can find it, and if you can find it, and if you can get NVIDIA to sell it to you, that can do like something like thousands of millions of floating point operations per second, floating point operations or integer operations per second, right? That comes in really useful when you want to render a video at a high frame rate, or when you want to play a video game once again at a high frame rate, or at a high resolution refresh rate, and so on and so forth. That component of hardware exists, but you still need to design software that kind of uses it. Fortunately, there's a framework for that. It's called like most people use the framework called CUDA. There's multiple in this area, but you can embed CUDA in pretty much any application, literally any desktop application, so that you can take select parts of your program and just give them to the GPU to process. And because of that, the CPU will have there'll be less overhead to using the CPU because it'll be less cluttered up than for the CPU in the main memory. That's one way you could utilize the hardware. Another thing that they support is there's sometimes these really complicated architecture level instructions for mathematically intensive procedures. For example, there's there's a kind of framework or a concept called XLA, right? Accelerated linear algebra, right? Where if you wanted to multiply two matrices together, or if you wanted to do, I imagine like row reduction, something like that, complex operations that are really important on the machine learning side, especially the deep learning side. If you wanted to do something like that at really high speeds, there's specific hardware instructions in your instruction set to support that. And one of the things that a compiler can do is optimize your code by using those instructions as opposed to the normal ones, right? That's actually a hardware related code optimization that's sometimes but not always possible. Google actually takes advantage of it a lot for their deep learning. If you've ever heard of TensorFlow for machine learning and deep learning, that actually uses pretty extensively this accelerated linear algebra kind of thing to look at your hardware, figure out what it's capable of, and like kind of compile your code specifically so that it really slams the hardware. It really uses not only makes it do the most work it can do, it also like uses the exact specific kind of instructions that are suitable to your workload. Those kind of advancements are made possible because of like kind of the compiler advancements that you have due to this hardware. Like I said previously, different advancements in hardware and advancements in kind of computer architecture make possible some advancements in computer compilers. If you have better low-level components, you start to design better high-level components too. That's actually a theme not only in hardware and compilers, but basically but basically software overall. If your backend team at a company is really good and they develop some new features, eventually the front end team is going to get with the program and evolve to implement that feature, ultimately resulting in a better experience for the users. So just that as a theme in software, like at the lower level, the more you improve, the more that effect kind of propagates upwards, and the more just the component of software becomes better overall, a better experience for the users. So yeah, the final part of this talk is going to be just regarding different concepts. I'll briefly explain kind of how the internet works. Aside from that, aside from that, I'll just talk about kind of networks at a foundational perspective, talk about how they're designed, what they're done for, how the original internet was designed, and just kind of the cool things that are going on in this area. So the first thing that I said mention on that list, network at a foundational level. Some talk about that. Network drive is basically an I/O device. Say this I/O device is enabled in this laptop that lets me have this video conference over Zoom and talk to you guys right now. It's on an I/O device, so basically a segmented memory equipped with its own CPU. Except it's not just anything. It's not the same as the other segments of memory in the coupled to the CPU. It's not like your main CPU or your disk device. It has the added capability. The key difference is that it has the added capability to encode and decode like radio analog signals, right? So your Wi-Fi signals and so on and so forth. Your Wi-Fi signals, your phone signals, so on and so forth. They communicate through. They are given through what's called like an analog, analog. So it's basically a kind of, you can think of it as a sine wave, kind of like a continuous frequency, right? It's one of the hardest problems that we've had to face as kind of humans in this area is figuring out how to represent a continuous kind of function or wavelength or what have you as a sequence of digital bits, like as a sequence of digital elements, right, as zeros and ones basically. So for lack of a more eloquent way to put that, a big problem is encoding analog signals as digital signals and decoding back, right? Because even though analog signals are the signals that are transmitted in like the physical world, digital signals are the ones that your computer can look at and understand and do something with. So at a foundational level, that's what a network device is. It's something that has the capability to encode and decode this analog signals. How it does that is like you need an electrical engineering degree to be able to describe it, to be able to like really give due respect to it, to really do it justice. But to be honest, all that I know and like all that you need to know to like kind of move forward in this aspect is to understand that an I/O device is kind of capable of doing that. This is where like we'll kind of move on to the software level. You'll see in this diagram that I have here that you might have seen this before in a systems programming class or an IT class. This is what's called the ISO OSI stack, right? I forgot what those. I can't remember off the top of my head what those acronyms mean, but it's a networking stack, right? It's a conceptual representation of how packets get transmitted, how data gets transmitted over the wire from segment to segment, from computer to computer, or from segment of hardware to segment of hardware, right? At the lowest level, you can see, I'll only go through like 4 of these. The top 3 aren't important for this kind of, for a talk of this theme, but at the lowest kind of 3 levels, at the lowest level, you have a physical link. So physically, like literally a wire, something that can transmit an analog signal, be that like whether that be over a wire as like, or just like as a frequency, or as a frequency communicated to the air. It's a physical signal, it's the physical layer rather, something that can transmit that kind of an analog signal physically. So at the physical level, it's one computer is responsible for sending the signal and another is responsible for receiving it at the hardware level once again. The next level, like it abstracts a little bit more than that. It talks about, multiple components, multiple computers connecting to each other. So instead of having like a one-to-one connection, you kind of have a linked list that like a doubly linked list, if you will. So that kind of like moves forward in that. as it kind of moves forward and backwards. That's also kind of possible at the hardware level. The next is like network level, where you have different networks, like different kind of subgraphs of computers that can talk to each other, and each of the subgraphs kind of link together over the physical and the data link layers to kind of formulate a supergraph, or like kind of an overall graph of like your whole network. There are subnetworks in kind of a super network, substructures in a superstructure. You can kind of think of it like that. And the most important one, the one that we'll be talking about most here, is the transport layer, which is its purpose is, as you can see, it's designed for end-to-end reliability, and it's the first component of the OSI stack that directly interacts with software, right? So at a foundational level, what goes on in each layer of the stack is that you parse a packet. And when I say parse, I mean parsing isn't in the same notion as a compiler might do it. You represent your string as just some data structure in your memory that you can reason about, right? And you parse the packet, and then you pass the contents of that packet to layer n+1, right? So the transport layer passes packets to the session layer, the session to the presentation layer, and so on and so forth, right? And at that level, once it goes to the application level and to the user reads that data, does whatever he wants to do with it. Maybe sends another 5 web requests before he does something else. But once he's done with it, he takes another packet, serializes it. Like you take a packet at some layer n, you serialize it, and then just pass it to the layer below it, right? To the layer n-1. So there's this constant kind of parsing it at one level, passing it up, serializing at that level, passing it back down. That's kind of constantly going on in networking. Networking makes extensive use of this abstraction, right? This notion that you can parse a segment of information at one level and pass it up, and the layers can kind of communicate with each other. And for sake of a good abstraction, each layer can only communicate with the layer directly above it, and above and below it, right? So once you have that kind of foundational understanding of networks, you can talk about some important metrics for gauging network performance, for being able to say whether your network is good or bad, it accomplishes what you want it to accomplish, something like that. The obvious ones are kind of latency versus throughput. There's a subtle difference here. Latency is kind of the end-to-end time, the time it takes for some request to go from your computer and kind of come back, right? The full round trip time. Whereas the throughput measures the exact time it takes on the server side, right? So once you pass a request and the server receives it, the throughput starts by measuring there up until the time where the server returns it. It doesn't gauge for the transmission in between. Like, it doesn't measure the transmission in between. Whereas latency, it kind of measures the end-to-end trip. It measures not only the throughput, but also the overhead for kind of transmission in between, right? Aside from that, there's also packet loss. There's some very loss critical, like stability critical, reliability critical applications that I'll go over in a second, that you need very low packet loss. You can't lose, you have to lose as little data as possible. Otherwise, that's mission critical. Otherwise, whatever you're using that software for, it doesn't work out. Packet loss is a very important metric in a lot of applications of networks. Aside from that, there's data rate. So that's another kind of obvious one. That's the transmission of that's the amount of data you can transmit per interval of time, right? So for example, like the link in my house, because I don't have fiber Wi-Fi, it's not available in fucking Edison yet. So you can, for example, in my house, you would get 400 megabytes per second. 400 megabytes per second is our data rate. Whereas a house that is equipped with fiber Wi-Fi, that would get 1 gigabyte per 1 gigabyte of transmission per second, or in some houses more than that. Or it's possible to go really high in that respect. I've read about networks that have 100 gigabyte per second data rate, for example. You could also do another really important thing to think about here are the different transport layer protocols, right? The transport layer being the first kind of layer that directly deals with software. There's a lot of the most important protocols that we'll be dealing with regarding computer networks are ones that kind of operate on that level. The most kind of yeah the most kind of the oldest and the most kind of tried and true ones. There's some other ones, but they're used mostly in research or for some very specific purposes, not necessarily commoditized use that you would see just going day to day. So the most common ones are TCP and UDP. TCP is the idea is that it's supposed to be. It's not the fastest thing in all cases, but it's a very stable. It's a very stable and very reliable connection. The connection protocol will guarantee that if I remember this correctly, the connection protocol will guarantee that once you establish a link, the packets will get sent in a certain way, and you'll receive the packets in the exact order that you receive them. And if you don't, it'll just start sending every packet over from the beginning, right? It's not always the fastest. It's not always the fastest thing, especially in cases where you don't have a high data rate or like a high latency guarantee. But it's definitely not always the fastest thing in all cases. But the characteristic that you're looking for when you use TCP is reliability, right? So when you're doing like something like an SSH connection or something like an SSH connection or some long running connection where you need a lot of reliability, right? The data has to go through in a specific way, in a specific order, and so on and so forth. So TCP maintains state at the hosts, right? So it maintains state to do that, maintains state to figure out what the order of the packets are, what order they should be in, and how to pass it to the user application in the desired order, right? UDP, however, UDP is like stateless. On the other side, it just kind of sends the packets and hopes they get there, right? And if the client reports that the packets weren't received, you just send them again. At a very simple level, that's what it does. There's no state that's really maintained on this client or the server aside from just figuring out which packets you did and didn't get. That's used for something like video transmission. Or audio encoding, where it doesn't matter if you missed a packet here and there. What's important is kind of the real time. What's important is that you get a continuous stream of packets as kind of reliably as possible, as opposed to getting them in a specific order or even at risk of certain time delays. There's a third protocol called Quick designed at Google that kind of mixes both. Like it provides UDP with some of TCP's guarantees. It's a good thing to read more about, but hopefully that gives you a good idea of networks once again, at kind of a foundational level. Finally, we'll talk about users. We'll talk about how networks are, how networks are used in kind of consumer computing, right? Just how we use them in our everyday lives. So, one thing that's important to talk about is the original internet was actually designed by an organization called DARPA the D stands for defense. That's all I remember about that acronym. But DARPA was an organization related to the military that was formulating the internet so that the army could communicate with itself, or different segments of the military could communicate with each other, right? At that point, they basically had, for military purposes, a lot of radio networks, and they wanted some kind of one paradigm to rule them all, right? They wanted a way to link the different radio networks to each other. So that's kind of the wavelength they were thinking along. When they first formulated the internet. It was most importantly a paradigm to interlink multiple disparate networks, like networks that usually communicate over radio signals or some other sort of analog signals. It's one thing that I do want to make note of is that it's designed for reliability over speed. And when I say reliability, I mean reliability over network partitions. So, for example, you have a case where you have a client talking to a server, and there's some n number of computers in between, right? If any k less than n of those computers go down, then that's what's called a network partition, right? Your packets might not be able to go through the network in the original way, so they have to reroute. They have to figure out something else. And in order to do that, they have to know that they're not getting through to begin with. That's actually, so TCP was actually the first transport level protocol that they designed under the ISO model, under the OSI model to like kind of formulate the original internet, right? What they did realize was that this abstraction was getting used more and more, this abstraction being the internet, and they reached some bottlenecks where TCP wasn't really designed for speed. Like the data wasn't really getting there fast enough in cases like like once again, like audio or video streaming, something like that, where you didn't need to, where the speed mattered more so than the reliability, right? So they formulated a second protocol, UDP, when they realized that they couldn't adapt TCP. It just wasn't working for that case. Right? They Once we look at that point in history, like once we look at that point, knowing as we do, like in our hindsight, that was such a important like founding moment in tech history. Like some people criticize DARPA for not being as thorough in all of this, like kind of looking at only like exactly what was in front of them as opposed to like kind of future proofing it and kind of generalizing it for all purposes as much as they could have that some, but but the internet's constantly evolving, and one of the things they're looking at is different design principles, different possibly even different transport layer protocols other than just directly TCP and UDP being the main ones, right? But that's just some history on how the internet was originally founded, and just to give you an idea of it should give you some kind of context, right, relative to how it's used today. So we have multiple different protocols for wired and wireless networking, right? At the most foundational level, we have what's called a Unix domain socket, right? So if you're on Linux and you want like one process to talk to another at really high speeds, those two processes being on the same node, the same computer, you would use a specific kind of socket, like you would use the Unix domain socket, right? At that point, it gives it to you really, really fast. It gives you stability and speed, but what you're guaranteeing is that you're not going over like a wire that's outside of your computer. You're going over like it's going to be on the same computer. You're not connecting one computer in say America to another computer in someplace else in the world. If you can make the guarantee that the two processes are on the same node, networking really just being this kind of paradigm to get two distinct and disparate processes to talk to each other. Those two processes can be being on the same computer in this case. Like this is something that will give you a really reliable and really fast connection rate, right? Aside from that, there's also just general purpose Wi-Fi. That's you can use wired Wi-Fi for high performance, or you can use wireless Wi-Fi for just you can use wired Ethernet. I mean, for just for high performance, and wireless Ethernet for just your generic use cases. But that's obviously the most common way in which we kind of use internet today. Aside from that, we use internet just as a network in that way. Aside from that, Bluetooth is actually a network connection. It provides like a very low level and very simple link between your host, your laptop or your phone, and your network device, right? So case in point, I'm talking on these headphones right now that I'm have connected via Bluetooth to my laptop. My laptop being the host and my headphones being the network device, right? And one thing that Bluetooth is really good at doing is it's good at kind of compressing on the fly. It's good at kind of compressing and sending really fast and really quickly and really stably. It's good at sending kind of compressed data, usually audio video streams, so that there's less to send over the wire. These headphones being an embedded device that's probably capable of decompressing the audio. You can send a compressed stream over Bluetooth over the network link, and then the headphones would decompress them. So that I could hear you, or vice versa. The mic on my headphones would transmit compressed audio as opposed to uncompressed audio, and my laptop would compress them. Right, that's a really neat feature of Bluetooth that's widely made use of, especially in the later versions of Bluetooth that offer some really nice guarantees in terms of, for example, in the latest versions of Bluetooth, one really nice guarantee is that I can walk like up to 35 feet, like I can go to the bathroom, which is like across the hall and like someplace else, and like my connection still wouldn't go out if I was still wearing the headphones. I would still be able to listen to Spotify or like watch my video or do whatever I was doing, right? Finally, there's the commoditized internet, the kind that we use for to Google things, to watch Netflix and so on and so forth, versus ad hoc physical and virtual networks. For example, in one of my grad classes, I was reading this paper where the application was telesurgery, right? And I'll talk more on this. What they couldn't use the commodity network because that wouldn't provide them the reliability guarantees they needed. So they set up their own physical network. They like channeled wire they channeled wire under the they channeled under the wire under the sea from like New York to France, and then use that network, like that network providing the reliability guarantees such that they built it themselves, right? They used that network to perform telesurgery, right? With the patient being in New York and the surgeon being in France, right? The surgeon was able to successfully pull out the surgery from France using kind of like remote tools that almost resemble kind of a video game. So so with that, I kind of wanted to bring up some open problems and just networking technology that like some cool things that we could talk and think about. Um, so one of the things that like I'm really looking into, this is actually my final project for the networking class that I mentioned. This is the final project for the networking class that I mentioned. It's a paradigm for kind of haptic feedback transmission. Haptic feedback being, for example, if you play like PS4, if you play Xbox, and your controller vibrates when someone hits you with an axe in Skyrim or something like that, you would your controller would vibrate, right? That's happening kind of over a network. Your PS4 is kind of running your PS4, your Xbox is kind of running your game, and that's the one that's kind of realizing that some guy hit you with an axe in Skyrim, and therefore sending a signal over to your controller, telling it to vibrate so that you can have that experience that you're having, right? That's some haptic feedback rather than it's communicating rather than audio or video, like kind of a motion, kind of a sound of the client device, like kind of a motion of the client device, right? In this case, vibrate. Or I imagine in telesurgery, actually it said in the paper that I was reading, it had it has a similar operation, right? When the guy hits an artery, it's kind of like a video game, like the controller kind of vibrates the closer he gets to the artery. This is also very as you can imagine, it would also be widely used VR or AR technologies. There was a lot of different. I interned at Facebook at some point in my life, and so I was able to try their VR headsets, try some brand of Oculus that some product in Oculus that wasn't really out yet. So one feature that it made extensive use of was this kind of haptic feedback transmission, right? It kind of vibrated against my head, and the controllers that I was using, they vibrated. And they did all these cool things. Because of haptic feedback transmission. So that's one thing they're making extensive use of. Aside from that, security is a very big open problem in networking technologies, especially as networks get bigger and more widely used. People are figuring out more and more ways to hack it. The kind of honorable mention here goes to the Azure's Internet of Things edge security systems. So what they have is they basically designed the system as visualized here, where there's kind of a Microsoft designed kind of execution environment that kind of sits on top of your existing execution environment and figures out what's secure and what's not, and only puts through the requests that it can guarantee the security of. So in that theme of guaranteeing security, there's also formal verification of this aspect, and I mean mathematical formal verification. You should be able to receive a spec for an extremely complicated system with for an extremely complex, extremely complicated system with multiple interconnecting servers and multiple network connections for multiple forward streams and feedback streams, what have you. And you should be able to formally verify the behavior of such a system. You should be able to mathematically guarantee that it behaves in a certain way and doesn't meet any edge cases. That's really important for some of the most performance critical applications and networks. So those are that should give you an idea of some of the open problems in networking. If you were to do research with one of the professors at Rutgers, for example, that research in this area, these are some of the things that you would be talking and thinking about. There are actually several professors at Rutgers that do actually exactly this. So that's actually the end of. This is the last slide. That's actually the end of the talk. Hope you guys learned a lot. Hope you guys got some different insights on how these different components of software and hardware interact with each other and how they are constantly advancing to push forward how we experience them as consumers. So yeah, yeah, good giving the talk. Hope you guys had